So are you ready?
Ready.
Can we start it? Okay. Good afternoon everyone. Thanks for coming. My name is Murilo Dourado and today I'm here with my partner Lucas Feraldi Pereira. We are both telecommunications engineering from Brazil, and as our home university in Brazil is a partnership with here this present university here in Germany, we had the opportunity to study here during 2 semesters, and now our purpose is to present you our bachelor thesis, which then is temperature management using web servers dedicated to the Internet of Things. This presentation should last about 25 to 30 minutes. If you feel free if you want to take any kind of notes during this presentation, and also if you got any question, it would be a pleasure to solve this question in the end of the presentation.
As the presentation was divided into 4 main points, I would like to start with a brief introduction of how the current scenario looks like concerning the usage of devices or sensors for temperature management that actuates through IoT platforms and has the capability to monitor or even change the temperature of the environment if the device and the web server contains such features. Furthermore, will be presented 2 different methods of how to construct an IoT temperature management system. Coming up next, tests that we have done using 4 web servers. Lastly but not least, the final analysis takes place in order to compare the solutions that we have found. Brief introduction. Let's start with the scenario. Nowadays, with the evidential growing of the technologies, when it comes to the temperature management, it's almost impossible not to speak about Internet of Things and its features. The usage of thermostats that can be connected with Internet creates a new world of ideas, possibilities, and accessibilities. Accessibilities for the physically disabled, we can provide better comfort for the final user, among others. And speaking about IoT, what does IoT mean? The Internet of Things, or IoT, refers to the billions of physical devices that are around the world that are now connected with Internet, collecting and sharing data. This allows devices to communicate without a human being involved and merge the physical and digital worlds.
But even though there are some challenges that still has to be faced off when we're talking about thermostat that can be connected to the internet. And the first challenge is the price. As you can see here, the price of this Nest Learning thermostat is around $250, and this other thermostat, which is held by Apple, costs about 250 euros. But not only the price, but also the interface is not so user-friendly interface. And the fact that your personal data might be managed by some company is not something really comfortable. So, with the purpose of testing different solutions and in using 4 different web servers to present our final interface to the user, we developed this research that points out specifically 2 methods.
Starting with the first method, in this case, using the 8R20 thermostat and constructing a master board. This method is indicated in the case that the user wants not only to monitor the temperature of the environment, but also change it, because this device allows such modification. Well, if we choose the 8R20 thermostat, we have the possibility to adapt and with an important extra feature, that is the radio module. This radio module will be coupled inside the thermostat that will communicate with an external source of information. Probably a master board that contains also another radio module coupled. This master board, now we are outlining here, can be represented either by an Arduino Uno or with an ATmega 128, which contains the function of to send the information to the node MCU, the Wi-Fi module, and then the Wi-Fi module will post the information online. For both cases, maybe use the so-called Open 8R20 source code, and for this, it's necessary to do some improvements. For example, concerning the oscillation of the crystal frequency, that is different depending on the microcontroller that we are using. So, the oscillation of the crystal frequency is 7.37 MHz in the case of the Arduino ATmega 128 and 60 MHz to the ATmega 328P. And also, it's necessary to change the pin numbers according to the new inputs and outputs and attending the requirements of the specific microcontroller.
Now we're going to present the second method, the method 2, using simple sensor. In our case, we are using the DHT22. Let's talk about a bit more this new sensor. This sensor brings with itself some pros and some cons. This sensor it's way easier to manage, as it doesn't require high knowledge in programming language to set them up. It's not required a master board, what also makes the project cheaper. But the cons are that this sensor does not have the feature of changing the temperature of the environment, and also is not as precise as the HR20. And as my friend Lucas said, showed the layout of the entire project using the HR20, I'm gonna present this layout for the sensor. First, we have the sensor that collects the data from the environment and sends to the node MCU, which has also the feature of posting the information online in the server. But here, it's really necessary to take a quick brief look at this arrow. This arrow is unidirectional. That means that the node MCU cannot send any message back to the sensor. So, in other words, the sensor in this case does not change the temperature of the environment. It does not have this feature. And with the intention of presenting the layout, the interface that we created, we used 4 different web servers that are Python Anywhere, Finger.io, ThinkSpeak, and FAGM. In this case, it is also necessary to stand out that we have to use the node MCU. So, independent if you're using the method 1, either the method 1 or the method 2, the usage of a node MCU is necessary.
And now, turning to the first web server, Python Anywhere, that receives the collected data of the sensor and printing in the interface. But how does it work? First, the DHT sensor will collect the information of the environment. Then, this information of the environment will be sent to the node MCU by means of a JSON data. And to reach the server, it's necessary to use the method called getJSON. And here, as expected, we have how the interface would look like. So we have the timestamp and all the values concerning the temperature and the humidity, as the sensor is also able to get the humidity of the environment. So here we can compare those values in the serial monitor and in the web interface. And you can see that this interface is indicated in the case that the user wants only to monitor the temperature of the environment. It's not a really user-friendly interface. We'll have here everything written in black and there's a white background. So it's sometimes quite confusing to check every line.
Now, let's move on to the second server, Thinger.io, the server that uses its own library, Thinger ESP8266.h, to post the information online. First, talking about a little bit of the source code in this Thinger.io. For every device, one credential is automatically generated and has to be set up into the source code. And also this source code presents an element called thing.handle. That is the element that establishes the connection between server and ESP. And if this element is suppressed, then the connection is also lost. And here, let's take a quick view of how does the web server looks like. First, we have how many devices is the user using, where are those devices located, and if you want to take a better look into the device, you have to go to the dashboard, and then you can see for how long has this device been connected, if the current status is online or offline, how many data was received, was transmitted, and also here this graphic shows the data that just received. It's not a graph in real time of the temperature, but a graph of the received information. If the information was received now, so there's going to be a peak here, and so on. There's also an open source platform ready to go, so it's really intuitive to work with this platform.
Let me move on to the third web server, ThinkSpeak. During our research, we realized that this web server could be a great choice if the intention is to get the information of the environment and plot it as a chart. So here, we need to use a feature called channel for this ThinkSpeak web server. And once that this channel is created with the desired title and the field, in this case the field is the temperature, we can follow the behavior of the environment in real time. And here we have an intuitive way to present it. Here we also can compare with the serial monitor, and we can see in the channel since when this channel was created, the last update, and also the last entry.
And lastly, but not least, the so-called FAGM. This server is by far the most powerful web server that we have faced off, and also was introduced by our orientator, Professor Werner. This server brings with itself a lot of different and useful features. And unlikely the previous server, this one requires a Perl interpreter running in a virtual machine or Raspberry Pi or whatever it is. In our case, we have this Perl interpreter running in our Windows 10 here. And also requires, for this server to work, it requires a broker that has to be working 24/7. In other words, unstoppable. And in our case, we are using the broker so-called Mosquito, that we are going to talk a little bit furthermore. So let me start present to you a little bit of the